A 2-decade journey in laser trapping, a micro step toward clean energy. Nearly 20 years ago, when we began this journey, clean energy wasn't on our minds. We were simply curious about human red blood cells. Their flexibility is essential, and we wanted to know. To explore that, we turned to laser trapping. Our initial goal was modest: apply force, observe deformation, and learn about the mechanics of life. But science has its own rhythm. To stretch the cells more, we needed more power. And as we increased the laser intensity, we noticed something unexpected. The cells began to twitch, move erratically, and then, suddenly, they would eject from the trap, almost violently, as if something had burst from within. After countless experiments, we discovered the cause: ionization. The cells were breaking down under the laser's intensity, accumulating charge until electrostatic forces launched them out of the trap. That changed everything. We developed a theory to estimate the radiation dose that triggers ionization, first applying it to red blood cells, then to cancer cells. The cancer cells took longer, revealing that our technique needed refinement. But the observation sparked a new question. What if, instead of ionizing a single cell, we could ionize an entire microvolume of blood? What if we could create plasma, a dense cloud of charged particles, and expose it to the laser's oscillating field? Could we generate electromagnetic radiation? Could blood shine? We tested the idea. For 2 hours, we exposed whole blood to intense infrared laser trapping. And yes, it radiated visible light. The blood glowed. That was a breakthrough. But 2 hours wasn't practical. We needed speed, so we turned to magnetism. When micromagnets interact with a laser trap, something extraordinary happens: a microscopic dark bubble forms. We first observed this during experiments with BT20 cancer cells mixed with magnetic beads. The bubble rapidly expanded, drawing in surrounding matter without letting anything penetrate. Trapped alone, the magnetic bead created a similar effect: a dark bubble that behaved like a capacitor, expanding when the laser was on, contracting when off, storing and releasing energy. More than 50% of the laser's energy was trapped inside, creating a powerful intensity gradient that pulled in surrounding material far beyond the range of standard optical forces. And then, at a critical moment, the bubble exploded. It incinerated everything nearby, instantly forming plasma. Suddenly, ionization was no longer slow. It happened in seconds, in volumes as small as 20 microliters. We had found a path to fast plasma formation and rapid radiation. That opened a new door. If we can create plasma in microvolumes, what happens when we scale it up? Can we ignite a larger plasma? Could it sustain itself, like a star, burning until its fuel is spent? Could we create an artificial star? In our lab, using just 200 microliters of bovine and horse blood, we saw early signs that this dream might not be so far-fetched. With the right technology to contain heat and stabilize the plasma, a self-sustaining radiant system seems within reach. And if that's true, what kind of energy could it release? Could we transform biological waste into power? Could this revolutionize the meat industry, not for food, but as fuel? And still, we kept asking, can inorganic materials do the same? This spring, I had the privilege of working with 4 brilliant undergraduates on a Eureka project. Together, we explored the interaction of micron-sized silicon, polystyrene, magnets, and yes, animal blood. The results? Light, plasma, radiation. What began with a question about red blood cells has grown into a micro step towards something greater. A new way to see waste. A new way to think about energy. A new way to light the future.